We begin with today's session. This is the lecture 4 in the first module, which is curves. And so we'll revisit what we have discussed so far, especially with regard to curvature, with regard to plane curves. So we began with the description of a plane curve, isn't it? So how should we define it? So curvature is essentially the deviation of the curve from the local tangential direction, right? And then we were able to obtain an expression for the curvature of a unit speed curve, right? And it is given by the double derivative of gamma with respect to t and take its norm, right? And say what if our gamma vector or the mapping of the curve is just any regular curve with no such special features such as being a unit speed curve. Then how do we derive the curvature function for such curves? Right, so we start, and the final expression is given here. Kappa is equal to the norm of the cross product of gamma dot and gamma double dot divided by the norm cubed of gamma dot vector. So we went on to derive the formula or the expression for this. Then we talked about the geometric interpretation of curvature in plane curves, right? So given that a gamma of S is a unit speed curve in R2, then we see that at any, so we see that at any point gamma S, the tangent vector is of course t vector, but there are two choices for the normal, right? And so there is when and in order to make our say so as to have a unique normal, so to speak, just for the purpose of analysis, we would want to define what we call as the signed unit normal of gamma vector as gamma as n of s. Right? So ns is obtained by rotating. So we take the tangent vector at the point gamma of s and rotate it by 90-degree anti-clockwise by pi by 2. And this gives us, and what we see is that since t vector is a unit vector, so t dot vector is going to be perpendicular to t, right? And therefore it is going to be parallel to ns. And we define a scalar kappa f, which is a signed curvature such that gamma double dot is equal to kappa ns, right? Ns vector. And the absolute value of this signed curvature gives us the curvature, which is kappa, defined as the magnitude of kappa s. And so that's what it is. So it just is essentially the norm of gamma double dot. But then what we saw is that it also requires that once we have the ns vector, but now what we are looking for is how do we define or how do we understand when the sign curvature is positive or negative, right? Since it has to have sign, isn't it? What we do is say we showed 4 different scenarios, and say as we increase the parameter s and move along this curve here, and at any point gamma of t, we have a tangent vector which is t vector, and using the more methodology that we discussed some time back, that the sign normal is going to be 90-degree anti-clockwise with respect to the tangent, isn't it? Right. So what we see is that in this case, kappa of s is greater than 0, right? And in scenario when we have just reversed the situation, that we are traversing the curve, or we have reparameterized some sort of, say, in a different manner, such that now progressing along this curve means we are following the opposite say direction, right? So we start with at this at this end and then proceed along the curve here. So the tangent is, of course, will be this t vector here. We draw ns vector, which is going to be perpendicular to t vector, and of course in the anticlockwise direction. Now, what we see is, in this case, the signed curvature kappa of s is less than 0. Right? And likewise, there are two different scenarios. So to understand how come, how do we say that the sign curvature is positive or negative, we have to we define such that if ns vector points in the same direction as r vector, and r vector is the radius vector, or maybe the point which, or the vector which connects the point of intersection of this osculating curve to its center, right? So this, if r vector and ns vector both point in the same direction, then sign curvature is greater than 0. And if, say, the r vector is anti-parallel to ns vector, then the sign curvature is going to be less than 0. Right? Right. So now what we say is, how do we define what is the geometric interpretation for kappa s? So kappa s has a simple geometric interpretation in that it tells us how the tangent vector, right? How the tangent vector rotates as we traverse the curve. Right? So if you're talking about some inclination, right? So say we have this curve here, and at any point there will be some tangent vector. Of course, we define a tangent vector, and if so, it makes some angle, say theta, with respect to x-axis. Say this is x-axis and this is our y-axis. S as we proceed along the curve. So this is how we define kappa of s. Okay. Now, if gamma of s happens to be a unit speed curve, then gamma dot s is represented using an angle phi of s, such that gamma dot s is equal to cosine phi of s comma sine phi of s. And this phi of s happens to be our, it can, of course, it may not be unique, because say if we subject this curve to a rigid body motion, right, or what we call as the um, what we will discuss later about isometric transformation, then this phi of s is not going to be unique. And of course, since we have gamma dot is parameter is expressed in terms of sines and cosines, which are periodic functions. So because that is another reason why we cannot have a unique phi of s. It will be unique provided we define some conditions, such that, say, at s is equal to 0, phi has to be some value. Then in that scenario, phi of s is going to be unique. Okay. So we propose that if, say, let gamma be a mapping from alpha beta to R2, and let it be a unit speed curve, and let S naught is an element of alpha beta, and let phi naught be such that gamma dot of S naught is equal to cos phi naught sine phi naught. Right? This is just some the tangent vector at the originating point for any curve, for some curve which we are defining over an interval alpha to beta. Right? Then there is a unique smooth function which maps from alpha beta to R, such that phi s of s naught is equal to phi naught. And of course, gamma s naught. Then in such scenario, we will have this vector, this tangent vector, which will be expressed in terms of sines and cosines being the x and y coordinates, right? And of course, I had referred to Presley's book for the detailed proof. Now let's also talk, I mean, we can also say, in order to define the sign curvature, what we would first we introduce something called as the turning angle of gamma vector. So the smooth function phi in this proposition, which is this proposition here, we have introduced some function called phi, right, which is a smooth function. It's also called the turning angle of gamma vector, and it's determined by the condition, the initial condition, which is phi at s is equal to s naught is equal to phi naught. And of course, as we'll see that it's since the tangent vector has some inclination, local tangent vector has an inclination of angle phi with respect to the x axis, then of course, as we move along the curve, and since we are looking at how the tangent vector is changing as we move along the curve, so of course it's anyway, it's also going to, the inclination angle of the tangent vector is also changing as we proceed along the curve, right? So that's the reason we call it as the turning angle, since this is the angle with which our tangent vector turns with respect to the x-axis, right? Now say gamma vector be a unit speed plane curve, and say phi of s be a turning angle for gamma vector. Then we define the sine curvature as d phi by ds. And sine curvature is the rate at which the tangent vector, of course, we have said this multiple times. And if kappa, and for kappa s to be positive, it is required that the tangent vector rotates anti-clockwise in the direction of increasing s. And for it to be negative, of course, t has to rotate anti-clockwise, has to rotate clockwise in the direction of increasing arc length parameter s. So then we talked to say, we introduced a corollary saying that stating that the total sine curvature of a closed plane curve is an integer multiple of 2 pi, right? Then we took a slight digression and talked about what we mean by isometry. And from the root words of this word itself, iso implies same and metry implies some sort of a length, right? So isometry is all that transformation which preserves the length between any 2 points of a curve in this scenario, correct? And this only happens if the entire curve is either being translated by the same amount, or if the entire body is made to rotate about some axis. Uh, yeah, the entire curve is being rotated about some axis, right? So in these two scenarios, we will always we will see that the isometry is being preserved, or I mean, it ensures isometry, right? Or that mapping happens to be an isometry, right? And what we have talked that let's since we define isometry for R2 as M, which is a mapping from R2 to R2, and M is a composition of two mappings, TA and rho theta. Rho theta is rotates. It rotates the. It is some sort of rotation mapping about the origin, and of course with respect to the z-axis in for planar scenarios, and it does so by an angle of theta about the origin and in an anti-clockwise fashion. And we say, provided we give we have the say the say a point in the domain xy. So and after transformation, it will assume the following form: x cos theta minus y sin theta, comma x cosine theta plus y cos theta. Just to check, what if this rotation matrix or the rotation mapping doesn't do anything? In that case, say if theta is equal to 0. Let's see whether we get back. I mean, since doing nothing, which means that mapping should give us what we had provided to it as an input, right? So what we say we put cos theta is equal to 0. Then of course cos theta is 1 and sin theta is going to be 0. So we get x into 1 minus y into 0. So that is x, and x into 0 plus y into 1 is y. So of course we are able to retrieve it. That's just the trivial mapping, right? and theta and TA denotes it's a mapping which applies a translation to any vector by a constant vector A. Right? In this case, TA vector is going to V vector plus A vector, and it will do so for any X vector, XY, and V vector in R2. Right? Okay. Then we moved on to talking about theorem, which we said we'll try to prove it in this session. So let's start with that. So let kappa be a mapping from alpha beta to R. And let it be any smooth function. Then there is a unit speed curve gamma such that alpha beta to R2 whose signed curvature is kappa. Now say if y tilde is a mapping from alpha beta from the interval alpha beta to R2, and if it's any other unit speed curve whose signed curvature is kappa, then there is a direct asymmetry M of R2 such that gamma tilde of S is equal to M of gamma of S. So this is what we we'll start with today. Right. So let's begin with this. So right. Now we will begin with the first part, right? So part one says that if given any kappa of S, so kappa be a mapping. So kappa is of course an element of R. Be a mapping from alpha beta to R vector. I'm using this notation which is being used a lot by Antman in his the pioneering book on nonlinear elasticity called Nonlinear Problems of Elasticity, right? So he uses such a notation. Of course, we don't require here. Yeah. So if it is any smooth function, then it says that there is a unit speed curve gamma from alpha to beta. Says alpha beta to R2 whose sign curvature is kappa, which is the smooth ones. So essentially we have kappa of S, right, is equal to for all. I mean, that is how the value of the function is going to be. Now say we take S naught is an element of alpha beta. And for any S is an element of alpha to beta. We fixed a point, right? Since that's how we have talked about, say, kappa of S is equal to d phi of S by ds, right? So then this we can algebraically let's manipulate it. So this will be equal to kappa of S ds, and integrating from S is equal to 0, which is, I mean, S naught to S, and this we have as d phi is equal to S naught to S kappa of U du, right? And so say that phi of S happens to be 0 at S is equal to S naught, then all that we have is phi at S is equal to S naught to S kappa U du. So once we have the turning angle phi of S, then the parametrization of the curve is given by gamma vector of S is equal to S naught to S cosine phi of t dt, comma so this from here the logic behind this is, since we know that gamma of S is going to be since it's a unit speed curve, I mean, since we want a unit speed curve, so for a unit speed curve, all that we require is that we express our tangent. Right? This is our tangent gamma of S is equal to cosine phi of S, comma sine phi of S, right? And then, of course, say we initialize, or let's say gamma vector at S is equal to S is equal to S naught. Say this is equal to 0, comma 0. Then what we do is we integrate gamma dot with respect to S. So then this gives us, say, S naught to S gamma dot, which is just d gamma by, say, dt into dt is equal to, again, this will have the same thing here, S naught to S cosine phi of t dt, comma S naught to S sine phi of t dt. Okay, and then after integration, all we have is gamma as a function of t, or in this case just S, is equal to integral S naught to S cosine phi of t dt, comma S naught to S sine phi of t dt. And we just and then we have to substitute the expression for phi from here. Right? So this will go here in the expression for the turning angle. So, and of course, and we can just take a look also. So if we take a derivative of y gamma with respect to S uh, and take its norm, that is of course equal to 1, which is anyway a unit speed curve. So we constructed it from beforehand itself, right? So this completes our first part. And anyway, the gamma units the unit speed curve. And furthermore, if we take d phi by ds, then this gives us kappa of S. So which means that this is what we had started with, right? This is the smooth function we are talking about, using which we built our curve, right? And what we'll try to do today is, like, we will we'll use this we are going to write some mathematical programs today, and that is where we will try to say, given any curvature, how do we define, or how do we find our curve, right? That's what we'll do. Now let's come to the part 2 of this theorem. So in the part 2, it says that if gamma tilde is a mapping from alpha beta to R2, and it is any other units curve whose signed curvature is kappa, then there is a direct isometry M of R2 such that gamma tilde of S is equal to M of gamma S. So this is what it's talking about. And again, since we say that gamma tilde is a unit speed curve, right? It is a unit speed curve. So the gamma tilde dot S is of course equal to cos phi tilde comma sine phi tilde S. Of course, there is anyway a parameterization which has been discussed in a proposition above. So what this implies is that phi tilde is a turning angle. for gamma tilde s. Right. So now what we do is this will also have gamma tilde by s, right? And this will be equal to kappa of s. So this implies that what we'll have here is that it's going to be phi tilde of s is again from s naught to s. This is equal to kappa of u du plus some phi tilde 0. Right, of course, we want some. In this case, we had defined it simply that say phi of, we had said that phi of s is equal to 0, s is equal to s naught is equal to 0. We just assume the simplest case, right? And in this case, we have say generalized it and considered some any arbitrary initial value of s naught, I mean phi naught, right? And this one thing, right? And here, this expression, if we integrate it, then what we'll have is, without making any assumption about the condition, about the value of gamma vector at s is equal to s naught. So upon integrating it, what we'll have is gamma tilde of s is equal to 0 to s naught to s cosine phi tilde t dt, comma s naught to s sine phi tilde t dt, and of course plus we'll also have some starting point which is gamma tilde at 0 or gamma tilde at s equal to s naught, and likewise here also we'll have s equal to s. Fine. So when we take a look at this expression here, so gamma tilde denotes, we just not to make it too cumbersome, then we drag it here. Okay, and just take a look here. So what we see that gamma tilde at s naught is a constant vector. So going back to the isometry that we had talked about, it says that there will be sequentially two steps. So this denotes the translation part. So translation by the vector, a vector of any v vector, right? So here gamma vector at s equal to s naught acts as that constant vector a vector. So it's essentially what we are doing is we are applying t, right? T mapping, of course, parameterized by the gamma tilde of s naught, and which it maps. All it does is it takes gamma tilde, or maybe this one, let's call it something else. So let it be gamma tilde bar, or maybe gamma vector tilde tilde. I think this just to, right? Gamma tilde tilde of s. That's what the expression is here. So what this does is it takes gamma tilde tilde of y of gamma, and then it just applies plus gamma tilde s naught. This is what it does. So it just adds this constant operation. So which means this is just pure translation. And it is applied to gamma double tilde, right? So one part of isometry argument is we have been able to do. Now let's go to the second part. So now let's consider gamma tilde tilde is a function of s, and then it has these two components, s naught to s, and of course it should be s here. Then cos phi tilde t dt and comma s naught to s sine phi tilde t dt. And let me make some minor, just for the sake of convenience. We can take this and let me call it some function psi of s. Just, I hope this is just for simplification. And let me also call this theta. And anyway, since s naught, no, phi tilde s naught is just a constant scalar, right? It's a scalar and it's constant as well. So theta is just some scalar. This is just for the sake of simplifying what we are doing here. So this means that theta tilde can be just theta, gamma of s plus, and this is going to be theta. Now what we do is we'll substitute everything in this expression here. S naught to s cosine, then we have phi of psi of s plus theta, and of course we'll call it d t here, and then comma s naught to s sine psi of t plus theta dt. Right? Now we'll use all those trigonometric identities of s naught to s. This we can call as, we'll expand cosine gamma of t plus theta. So this will be cosine gamma, cosine psi t cosine theta minus sine gamma psi t into sine theta dt, comma s naught to s sine psi of t cosine theta plus cosine psi of t into sine theta dt. So this is what we have, and let's further expand it. So this will give us integral of s naught to s, and what we can do is we can have cosine theta into s naught to s cosine phi of t psi of t into psi of t into dt minus again sine theta s naught to s sine of psi of t dt, comma, let me just make some room here because likewise what we'll have is cosine theta. I'll just rearrange sine theta of s naught to s cosine phi of t dt plus cosine theta s naught to s sine at psi of t dt. So I think things are falling in line. Now what we do is, I hope you may have noticed a pattern here. So the pattern is that, let's take a look at the expression for this case. And of course, I would not even have need to call it psi. I was just starting with psi of s. But when you take a look at psi of s and phi of s, they have the same expression, right? So even we started with something which is not known, and just now we are trying to reduce into to some other phi of s, and then what I'll do is just for this we have phi cosine phi of t, phi field. Right. Now let's take a look at the coordinates, x and y coordinates corresponding to gamma of s. So gamma 1 coordinate is s naught to s cosine phi of t dt. And take a look here. This is the same, right? So this is gamma 1. Again, from s naught to s sine phi t dt, which comes here. So this I can also write it as cosine theta gamma 1 of s minus sine theta gamma 2 of s comma sine theta gamma 1 of s plus cosine theta gamma 2 of s, and this is going to be gamma tilde tilde vector of s. Now let's go back and look at the rotation isometry that we had. Rotation part of the isometry. All it does it does x cos theta minus y sin theta x sin theta plus y cos theta. Isn't it the same? X cos theta minus y sin theta. So this is as if we are applying rho theta over gamma vector of s. And to be more precise, theta is phi tilde s naught. Now combining both of them. So combining this with this here. So what I'll say is, so combining one and two, we have gamma tilde of s is equal to t and gamma tilde at s naught of gamma tilde tilde s, right? This is again equal to gamma tilde of s naught into rho phi tilde of s naught to gamma vector. And of course, this can be simplified as t, I mean, just for the sake of representing here, you can have rho phi tilde s naught, this acting over. This is what is isometry map, right? This is isometry, so of course. So we have been able to show, right, that provided we have the smooth function kappa of s, and initially we were able to construct a unit speed curve, and say if we had any other unit speed curve, then the goal was to obtain the isometry which relates both these unit curves. Right? So that is what we're talking about. Okay, so what we will do now is, let's begin with space curves. Let's start a new topic today. Space curves. So far we have been dealing with, so far we have been So far we are dealing with planar curves, but as we know that curves are in general always lie in 3D space, and so curves in general lie in 3D space, right, in R3. And although it was a good point to start with planar curves, that we got to understand that planar curves was a good start, right? To good was a good start to uh, planar curves. What plane curve that we call it is say is a very good beginning with a good starting point to understand uh, the space curves. So plane curve by definition it always exists in a plane. The thing is it will always be contained in a plane, and in of course it will always belong to the set R2, and space curve belongs to the space R3. Now plane curve, although it's I mean it's very simple, so to speak, to analyze as compared to space curve, they do tend to have a lot of applications. As an example, say you have a pulley, right? So one part of this is say a person is trying to pull it down. So there's just some schematic, and there is some load here. He's standing at a higher pedestal, and this he's trying to carry to bring this to his level so that he can just take a hold of it, right? So this force is being applied in this manner. There is of course fixed. So when you look at this curve here from the side, of course it is a planar curve, right? Just an example of wherever we see. Not only, I mean, this is just some in terms of some some physical body. It happens to be some physical body. Now, say when you study a conveyor belt driving two shafts, and you look at the motion, or even just at the default and just at the geometry, there is also a planar curve. Although in 3D, of course, it's a strip. Conveyor belt happens to be a strip of some finite thickness and of course finite width. But yeah, from the side, it does the cross section through the this major part or through the length. It looks like a planar curve, right? So the representation of this can be described in terms of a planar curve. So these are, of course, these are physical objects. Now, for things which are not physically, they are not objects per se, but they do tend to have that geometric understanding, is when you say you pick up a ball and just launch it into the air, right? So it does follow some trajectory. Of course, it will fall down somewhere, provided we are not as strong to throw it at the speed of more than the escape velocity. So till that point, it will obviously return to the ground. So when you look at the trajectory taken by followed by the ball here, that is a planar curve. So in all these cases, gamma vector was a function of the arc length parameter S. So this was arc length parameter in this case as well. In this case, gamma vector happens to be a function of t, and t is time. So although it's not any physically, it does not, it's not a curve, like you cannot touch it. So, I mean, in that sense. But however, from the representation, it has that curve-like features, right? It does have it. We can understand this as if we are dealing with some curve, right? Okay, so that was some of the examples here. But for curves in general, like in space curves, say when you are dealing with say twisting of some, say you take a wire or some thread and you just apply torsion, twisting at both the ends, then uh, then what it will do is it will tend to form some localized shapes like this. Now you see this is no longer 3D. I mean, no longer 2D. It's a 3D phenomenon now. So the deformation is 3D in nature. So which means this makes it so crucial to study space curves. And of course, in differential geometry, that's what we are talking about. We are talking about the studying or analyzing or understanding curves and surfaces. So curves always mean space curves. And what we'll see is that planar curves, plane curves are just a subset, a special subset of spatial curve, I mean, space curve, right? Okay, so to define a plane curve is determined of course to the point of isometry by the curvature function. And we'll call that any, say you have a curvature function, you can always construct a unit split curve and then determine the curve, right? And there also, and any other unit split curve is going to be just an isometry of this. So it looks like till the point of isometry, we always have one unique curve determined by the curvature function. However, in space curve, it's no longer, you cannot just obtain with the help of, we cannot just obtain with the help of curvature function. We also do require what you call as the one more function. So space curve are not, is not or cannot be defined just using cup of S. It requires another function, another curvature called torsion. So this torsion is what we are, which is the new addition to the problem. And so what it implies that curvature, the one that we have understood so far, plus torsion results in a space curve to the point, of course, up to a direct isometry. R3. Fine. So it looks like we need one more quantity, torsion, and then we can be able to obtain a space curve. Okay. So let's try to define all this. Like let's try to properly build the necessary ingredients to for a space curve, right? So we begin with that. Okay, let gamma vector of S be a unit speed curve. We always consider any curve to be unit speed just because of the additional advantages it has. Not just it has lot many advantages, and which makes our calculations quite simpler. And although at the same time, knowing that it's not very easy for all the curves, of course, every curve does have a unit speed parameterization that is guaranteed, but many a time finding finding it explicitly is not an easy job. Okay? So let gamma be a unit speed curve in R3, and let T vector is equal to, T vector is equal to gamma vector be its unit tangent vector. Now, if the curvature kappa of S is non-zero, then the principal normal let me highlight this here as well. This is a very important thing. Let's call it. So the principal normal of gamma vector at the point gamma vector is tan vector of S is equal to 1 by kappa of S and T dot vector S. So principal normal, that's a new word that we have discovered today. So principal normal of gamma, right? And the question is, okay, how do you define it? Okay, so we first say it's a slight digression, but I mean, it's of course we do require it to understand it. Since gamma vector is a unit speed curve, right? So this implies that the tangent vector has a norm 1. If we square it on both sides, we have gamma dot squared is equal to 1. And this implies that gamma dot is equal to 0. Is equal to 1. Now differentiate both sides. Differentiate both sides with respect to S. Then what we have in our hands is 2 gamma double dot is equal to 0. So this implies that gamma double dot is 0, and which means that gamma double dot is perpendicular to gamma dot. So because it's perpendicular, so which means that there must be something which is normal to the tangent. Right? It's so say gamma double dot is perpendicular to gamma dot means gamma double dot must be parallel to something with a vector which is perpendicular to gamma dot, right? So which means that gamma double dot must be parallel to n vector, and n vector is, say, perpendicular to gamma vector, and n vector is also a unit vector. It's a unit vector. So, however, to relate both of them, we do require some function. It is parallel, but there must be some multiplying factor, multiplication factor. Right? So we just call it kappa of s, and that's it. And of course, gamma double dot is the same as t dot and kappa of s. So that's the reason we have been able to obtain. So this arrives from this point here. You take the rest, divide t dot by kappa of s, and then we have the expression for n of s. So that's how we arrived at here. Right. And we can, there is one more thing to say, that so the norm of t dot, of course, it's equal to the norm of gamma double dot. This is equal to kappa of s, signifying that kappa of s is always going to be greater than 0 by definition. And of course, we would not want kappa of s to be 0, because then n of s is not defined. And later we'll know that in what we are discussing right now is called as Frenet-Serre frame. So kappa of this is a major disadvantage of Frenet-Serre frame, that it does not allow kappa to be equal to 0. Otherwise, we cannot have we cannot define the principal normal to the curve at any point gamma of s. Right. So since t vector and n vector are orthogonal or unit vectors, and they are mutually orthogonal, right? Sometimes it's synonymous to perpendicular, but yeah, there is some subtle difference which we'll discuss about it later. They are mutually orthogonal to each other. We define a unit vector which is perpendicular to both n vector, both t vector and n vector. That's what we are doing here. To both t vector and n vector. And of course, cross product of two vectors give us a vector which is perpendicular to both, right? So that's why we have b vector is equal to t vector cross n vector. Now, b vector of s is called the binormal vector of gamma vector at the point gamma vector of s. So there is another new word here. So essentially, we have thus we have an orthonormal basis of R3 and which is also right-handed. So that means T vector sequentially N vector and B vector. This is our orthonormal basis. And it's also right-handed such that T vector cross N vector is equal to B vector. And then N vector cross B vector is equal to T vector. And what we have is B vector cross T vector is equal to N vector. So that's what we mean by the right-handed coordinate system. Okay. So we have come this far. Now, as B vector, as it's a unit vector for all S, then of course, from the rule that B vector dot, so B vector dot B vector is going to be equal to 1. And differentiating with respect to S, this implies that B dot is equal to 0, right? With respect, differentiating with respect to S. So which means that B dot vector is perpendicular to B vector. So this is what we are looking at, right? Now look, going back, we have B vector is equal to T vector cross N vector. So since B vector is equal to T vector, differentiating we have V dot is equal to T dot cross N dot plus, this is that chain rule, right? T cross N dot. Now recall that T dot is equal to kappa of S N vector T of S. So which means that T vector, of course, is parallel to N of S. So this means that the cross product of T dot and N is going to be 0 vector. So this implies that V vector dot is equal to T cross N dot vector. Right? And now what we see is we see that B vector is going to perpendicular to T, of course, right? And also N dot. Right? It's going to perpendicular to both, right? So, and also N vector dot is perpendicular to N. And that's by design, isn't it? It has to be perpendicular. So, which means that N vector dot can be expressed as some, let's say, function alpha of alpha of S into T vector of S plus beta of S. These are some unknown functions which will give it a name later, but let's try to determine the expression first, their forms first, right? Into B of S. This is what's going to be. So putting this here, what we have is beta vector dot is equal to T cross. So maybe I'll just say star into maybe double star into star. So substitute and this, let it be always be stored. Sorry. A very important quantity. So let it interact and then right. So substitute double star in star to get V dot is equal to T cross alpha of S plus that. Now T cross T is, of course, I mean, anyway, let's first write it. T cross T plus beta of S T cross P. So this is, of course, equal to 0 vector, T cross T. And T cross B is equal to, from the right-hand coordinate the rule, right-hand rule, it has to be minus M. So it will be minus beta of S and then N of S. Now this beta of S is called torsion and it is represented as beta of S is equal to tau of S. This conventionally, this is how we represent it. So therefore, B vector of S is equal to minus tau of S N of S. Let me also color this in black. Sorry. So here we go. Okay, so B, the expression for B of S, beta of S is known. Now what we would want is now N vector dot of S is equal to alpha of S T of S plus beta is now tau, so tau of S. Okay. So what we do here is let's take the expression that we had like this. We can differentiate with respect to T, but Okay, so let's try to do some. So what we do here is, so n vector dot n is n vector dot is equal to 0. This is already done. So let's try to. Now, since n vector is perpendicular to t vector and n vector is also perpendicular to b vector. So we have n dot, like since this, and then we have n dot t is equal to 0 and n dot b is equal to 0. And say differentiating both with respect to s. So it will be n dot t plus n dot t dot is equal to 0. Likewise, n dot b plus n dot b dot. Right? So when we take a look at here, so n dot b, n dot b, n dot b is equal to tau of s plus n dot b dot. N dot b dot is equal to minus tau of s. This is of course identically satisfied, so nothing to gain from here. So what of this? What should we do of this? So n dot t is n dot t, n dot t is alpha of s plus, so here is the main point here. N dot t dot is what? So n dot t dot. So multiplying both sides, I mean dot product both sides with n dot, with n will give us kappa n dot n dot t dot is equal to kappa s n dot n dot. So n dot is just one. So we have this will just be kappa of s. So which means that alpha of s is equal to minus kappa of s. Right? So therefore we have black n dot of s is equal to minus kappa of s ds plus tau of s and v of s. This is what we are looking at, right? So finally, let's summary is what? So summary is t dot of s is equal to kappa of s and vector of s. Let's try to slightly adjust this. Then we have n dot of s is equal to minus kappa of s t of s plus tau of s b of s, right? And finally, b dot of s is equal to minus tau of s. So I'm just writing in this form because, yeah, it's easy to, in matrix form, say in linear algebra, that's how we often tend to do. So in matrix form, we can write it as d by ds of t vector of s, n vector of s, and or maybe why not do it vertically? Yeah, we'll write in both forms. So let's write in both forms. So so let's look at the d by ds of n vector of t vector. So it is equal to 0 kappa of s 0, right? Now n of s. So this is going to be minus kappa of ts. So minus kappa s of ts, and plus, of course, 0 plus tau of s. And for b of s, we'll have no contribution from ts, contribution only from n of s. No contribution from b, of course. So this is just a form of writing. The thing is, this is much more elegant in to say that since t vector and vector b vector, when we represent in the Cartesian coordinate system, they are going to be column vectors, right? That's how we represent a vector. Another way of representation is like, but this is not very say mathematical. It's not as mathematically elegant. Maybe from an operational point of view, I'm saying. So this can be like, so in this case, we have to pre-multiply. This looks very nice. So we'll have this set as well. T of s, n of s, b of s. So t of s, 0, kappa of s, then 0, n of s. So minus kappa of s, 0, and then tau of s. Likewise, for b case, we have 0, minus tau of s, and then 0. Yeah, they are, so to speak. But yeah, this is more user-friendly from a mathematical point of view. It's much more operationally friendly since t vector, n vector, b vectors are column vectors when we represent them in Cartesian basis. Okay. So now what we do is, so this one was, we specifically wrote it for a unit speed curve. But what if we want it to be more general in nature, so to speak, right? So what if, or maybe, or when the gamma vector is a regular curve. That is, gamma vector will be maps from is equal to gamma vector of t, and it's not a unit vector. In that sense, how do we define all this? So I will just write down the final expression because that's what is going to be useful essentially. So say when we write the say gamma vector of t is equal to say some gamma or say s of t. And this is going to be, let's just call it some gamma tilde of s of t, right? Just so d gamma dt by dt is equal to d gamma by ds into the end. This let this be the unit speed parameters. Or maybe I believe that to remove all this confusion, let's just take this to be the tilde, right? Yeah. So when say gamma is a regular curve, right? So gamma tilde, and then we can express in terms of this, right? So when we take with respect to t, then this will have d gamma by ds into ds by dt, right? And the norm, taking the norm on both sides. So take norm on both sides. We have what we have is d gamma by tilde by dt, and this is equal to, at of course t. We write it nicely. So d by dt is equal to d gamma, of course, at s ds and ds by dt. So this gamma here is a unit speed reparameterized. And of course, the norm of this, which is just the magnitude. And the way we define it, we always take ds by dt to be in a manner that's positive in nature. So this is, of course, equal to 1. So this implies that ds by dt is equal to s dot, and this is given by d gamma, or maybe just gamma tilde t dot, right? Gamma tilde t. So which means that the tangent vector in this case was gamma tilde t. So then what we have is that gamma tilde dot t maybe just to remove any confusion, let's take prime indicates with respect to any other parameter is equal to, so I should have called it so gamma vector tilde is equal to s prime as a function of t into t vector t, or maybe just call it capital T vector. So this is just to indicate that not to any confusion, right? So just to remove any confusion. So this anything primed indicates difference with respect to t. So gamma t is equal to this, right? So this is for the tangent, and of course, the way we define the curvature. So for curvature, what we have is so we define the curvature as kappa is equal to, this was gamma double dot with respect to s, right? And when written in terms of like arc length parameterization, what we mean to say here. So this is in with arc length parameter. However, for this we'll have as gamma tilde double dot t, take the norm, divide by s prime, s prime of t. So this is how we define kappa. And of course, t vector, t vector t is equal to s prime of t. So this is also equal to of s prime kappa t and then n vector t. So this is for the t prime case, and following the same strategy that we have been dealing so far, the n prime, it's just a matter of reparameterization. So this will be equal to minus s prime t kappa of t and t vector plus s prime of t tau of t, and then we have b vector of t. Likewise, so similarly, using all those properties, we'll have b prime of t is equal to not minus, just s prime of t tau of t, then n vector of t. So these are the say the three differential equations to determine the basis vector when it is not for any general regular curve. Now, since we have all that, so let's say derive the expression for curvature of t using only using the just the mapping gamma tilde as a function of t. Okay, so given that we have the expression for So this we have here, right? So let me just put it down here. So this one was equal to S prime of t, and this one would represent something called as a tangent vector essentially. So it is, so we will have, let's just put it here. So since this norm is 1, right? So this one, it represents the tangent vector. So we can write it as ds by dt into some tangent vector t. Of course, we'll have gamma tilde prime t is equal to s prime as a function of t vector t. Now differentiate with respect to t to get gamma double tilde, double prime is equal to s double prime of t into t vector t plus s prime t into t prime of t. Right? And as we recall, since we have the expression for this as well, so s double prime t, t prime t plus t prime t is s prime kappa. So it is s prime t whole squared kappa t and then n vector of t. Once we have this, now what we do is take the cross product of gamma prime t and prime double prime t. So in this case, double prime. So first term t dot t is 0. So the first term anyway it doesn't make much difference. I mean, it evaluates to 0. So in the second case, s of t, right? So in the second scenario, we have s of t, s prime t was into s of prime t squared. This gives us s prime t whole cubed, right? And then t cross n is b. So we also have this kappa of t. And t cross n is b vector. Right? So taking the norm on both sides. And since the norm of b is 1, so what we'll have is the norm of b is 1. Anyway, let me just write it down. So therefore, kappa of t is equal to norm of cross and it's divided by s prime t. And as we recall, s prime t is also the norm of gamma. So the gamma prime t, right? So which means that we can just divide this by gamma prime t and cubed, sorry. So now we can see why do we require the curve to be regular, right? Because for a regular curve, gamma prime of t is not zero vector, right? So that's the reason. So this is a general formula for, and this we can use to determine for any case, be it regular or non-regular. I mean, be it unit speed curve or non-unit speed curve. If it's unit speed curve, then the denominator becomes 1. And of course, then gamma prime is perpendicular to gamma double prime, which means that the norm of the cross product is just the equal to the norm of gamma double prime. So that's it. Right? And secondly, we would also want to derive the expression for the so our goal was to determine the no, on the same lines we have derive the expression tau with the torsion using just gamma vector and of course its derivatives. This is done. So what we start is we already have gamma prime and gamma double, the expressions of gamma prime and gamma double prime. So now we have gamma, that's gamma triple prime of t. So this is equal to, so we use this form here. So this will be equal to gamma triple s triple prime t vector plus s double prime t prime vector plus the first term. So add 2s prime t s double prime t kappa of t n vector of t plus the second term, the chain rule, right? So we have s prime t whole squared kappa prime of t and then n vector t. The third term, I mean, kappa t and n vector t. Okay, so we need to have here, we need to put in the expressions. So t of t and t prime of t was s prime kappa t and t, right? So s double prime t s prime t and kappa t of n vector t plus 2s prime t s double prime t kappa t n vector t plus s prime t whole squared kappa prime t n vector t plus s prime t whole squared kappa of t, and n prime is given by minus s prime t kappa t and t plus s prime t kappa, no, sorry, tau of t and then v vector of t. Okay, so let's bring it to this side. Right? Okay. You would want to rearrange things, everything in terms of t. So the first term and this term as well. So minus st whole cubed kappa t whole square t vector t. Sorry, this goes t vector t. And likewise for n we have s double prime t, s prime t kappa t plus 2s prime t and s double prime t, right? So eventually it evaluates to this becomes 3. So 2 plus 1, 3. And what we have here is plus s prime t whole square kappa prime of t. And yeah, this goes with n vector. And for the last term, we have plus s prime t whole cubed kappa t, right? S prime t whole cube kappa t tau of t. And so kappa of t is equal to the cross product of gamma prime double prime divided by gamma, the norm of gamma prime t cubed is just s prime. So which means that this cancels out, right? To have everything in terms of t plus that in terms of n. We would not want to write it because I will say that it just cancels out, or maybe not. So this is plus. Let me make some more space for. So we have the norm of gamma prime tilde prime t cross tilde double prime t, sorry, tau t and b vector of t. Prime. So let's look at the term gamma cross gamma prime cross gamma tilde double prime. So this is what we're talking. So what happens here is let's take the dot product of this with respect to this. So take the dot product gamma tilde prime cross double prime t with gamma tilde triple prime of t. So in this case, what happens is, so why not write it down first? Copy, paste here, screen. And for this as well, sorry. Copy this as well. We could have otherwise just left it as it is. So I had to use let use this later. Before that, let's just call it S prime. So we have this, right? And then take this dot product with this big term. Now b dot t is 0, b dot n is going to be 0, and b dot b is equal to 1. So this gives us S prime t cubed into and then cubed again. So we have 6 kappa squared t, and b dot b is 0, 1, and then tau of t, tau vector, not vector, tau. So we're able to, we're able to get this such a simple expression. And so this implies that tau of t, and this can be written further as, since kappa of t into S prime, I would just call it cubed into squared. So S prime in cross S prime cube kappa t cube squared is equal to the norm of this squared. Just drag it down and put it here. Square of tau of t. So therefore, this implies that this is equal to a lot of copy paste work here. This, this, this is what we are looking at. So we have the expression for torsion. So yeah, we are able to describe, get the expressions for both these terms. So what I feel is like, okay, let's continue the discussion and finish this curves part by the next session, and then we will do some problems in mathematical. So yeah, I think we could not be able to do today. It has been quite heavy work. So yeah, so in the next session we will be dealing with about continuing our discussion further on curvature, and then we had already discussed about Frenet frame. So this T and this forms what we call as the Frenet frame, and we'll put it in better words in the next session. Yeah, and we'll also try to talk about some advanced, say, properties of curves before we move on to the surfaces if possible within the next few by the next session. Okay, so this equation that we had talked about, right? This one. So this is also called as Frenet equations. Here and then. And this they form, and this T and S. Right? So T of S and S. This is the framing. Save frame. Okay. Yeah. So yeah, I think with this we end today's session. Let's meet in the next session tomorrow. Right. I'll just close the session for today.